people often confuse or misrepresent the connotation of deep learning in respect to with respect to machine learning and AI. Like umpteen times people use these definitions of these technologies interchangeably. So what I want from you right now is a description of what deep learning is and its relationship with AI and machine learning.
Okay. I think the it's first of all just understanding the main difference between what is difference between AI, deep learning, machine learning. So AI is like a complete system which has this machine learning and deep learning algorithms in it. But it is an AI system will be like a full development system which will have other kind of pipelines or things. Whereas deep learning, they are like kind of an algorithms. Machine learning is also an algorithm kind of a things. And when you come to the difference between a deep learning and machine learning, it's like they say that machine learning is like in a simple algorithms such as like the SVMs and stuffs. Now even a single layer perceptron is also accepted as a machine learning algorithm. And on the contrary, deep learning is like a multi-layer perceptrons are deep learning things. So yeah, that's a difference which people talk about.
I would like for you to go in a little bit more depth about how deep learning works, as in like probably talking about neural networks, how they are built, you know, probably talking about back propagation and how the iterations with different iterations, the model improves itself, and in general how to build a deep learning algorithm or a neural network framework.
Okay. So basically, to start with, there is this a basic problem which everyone tries to encounter, tries to solve, is the linear regression. So the whole ML models which are based, or the artificial neurons which are based, they are completely based on this problem to solve a linear regression problem. Okay, and on this we have built up various functions to solve this, various methodologies to map upon things. So getting to started with how do we build a neuron. So firstly, understanding what we try to solve. We try to solve a mapping problem kind of a thing, where we have a given input and we need to see that what exactly there could be a function f of x which will just map the given input to the given output, and we try to approximate that using a linear regression. So when we come to a machine learning algorithm, we first we see that how the algorithm tries to learn all of these things and get an estimated function value. When it comes to deep learning, the deep learning, we have something called as a perceptron. A perceptron is something which takes multiple single input or a multiple input, have a function f of x, which gives an output, which gives a prediction of an output. And this f of x is a black box, which it tries to understand based on the given inputs or the given training data. So a simple algorithm will be feed in the input, the f of x learns upon it, and it tries to estimate the whole thing. And when it comes to deep learning, we have this multi-layer perceptrons. There are like multi-layers of these neurons which are just attached and connected in various formats and in a various manners, so that we are able to approximate f of x. So coming to the part that what is a backpropagation thing, backpropagation is like um, the given f of x is trying to update based on the so there's something known as a loss function. A loss function is something which tries to we try to optimize like a given function, our f of x, which we want to see what it exactly has to be optimized into. So here the backpropagation takes in picture, where it tries to take in the output of the earlier perceptrons in pictures to optimize the given function. Yeah.
What currently is the biggest pain point in regards to the development of these frameworks or in general just advancing this technology?
You mean the deep learning and stuff? I think like they are already at very par. They like this these technologies are very much came into the picture, and right now people are developing electronic circuits or trying to find out methods and how this could be made in a very sustainable way. And the other format is trying to understand the expressibility of the given AI models, of really understanding. It's like the uncertainty of the black box is very much not like what people don't want to understand. It's like, let's say you are in a medical field and you want to, like, okay, your AI model is performing well, but to understand, is it really performing the way it is? So to understand this AI thing is what the current field is. But with regards to the technology, the algorithms, we are way too ahead. We are way too ahead. And NVIDIA's QDNN was like one of the method, which, like, not method, I would say, one of the technology which enabled us to like take the exponential leap over here. So yeah, but with regards to that, it's we are way too ahead, I feel, and there is still more to come.
So probably then the next current advancement or studies being conducted in how to utilize this technology to advance some other technology like quantum computing, which currently is at a very developmental phase or a very rudimentary phase in regards to how applicable it is to solving actual real world problems. So I'd like for you to elaborate upon the utilization of deep learning and AI in regards to the development of quantum computing.
Okay. Uh, Regards to that, so basically, what we see is we use AI to understand some black box things, or some things which need to be computed very faster. So, quantum computers, when we say that it's not fully developed, it's all because of, theoretically it is we have understood a lot about it, but when it comes to a practical point of view, the circuit doesn't, like, the hardware doesn't support the way we want it, because of there are a lot of noises. And what we see is there are different methods of error mitigations and error corrections. So right now what researchers are doing is they're trying to put in AI to help in this, in terms of error mitigations, error corrections and stuff, and how it could just accelerate the whole thing, where we don't need to devise our own f of x. It's itself is trying to devise it by its own, and then it we can produce this model. One good paper, I would say, and this is by NVIDIA, which they have recently published, is a GQE, generative quantum eigensolver. This paper, they try to just have a generative circuits on how, and ansatz could be there, and that could be optimized very well on a quantum system. So as per what I have understood correctly, so that this is a one of a way you could see that how generative AI is taking in picture in quantum technologies, and it is helping the quantum computing to boost up. Because yeah, we can't actually right now, I myself am not able to visualize anything pure quantum. It's like there is a coexistence of classical and quantum. Even there's a recent paper by IBM, which a quantum centric supercomputing, which they have seen, which is also goes with regards of existence of classical and quantum, and the processing power of classical should match with the processing power of quantum. So that's how we will be working towards the utility of in this field, of how really quantum computing will be very helpful. Yeah. um,
Um, Also, what are the current challenges in integrating probably deep learning or the AI technology and quantum computing? Maybe this in regard to the scalability part. Like we know that there's a lot of noise and fidelity issues and decoherence, but like what is the true complexity of these hybrid models? Because you did talk about something very important, that currently we aren't able to develop fully or completely realize the potential of purely quantum systems. So we need the assistance of classical frameworks to sort of amalgamate a framework that has the essence of quantum and the support of classical. So what are the problems and challenges with that, and what are we doing to solve those?
Okay. With regards to when you say about integration of a deep learning and quantum, so there is like two aspects. One is like deep learning for quantum computing, and one is quantum deep learning, or let's say quantum AI. So let me first address the deep learning for quantum. I think which I had did address before, that how we are trying to be helpful in that, and that is the most of the research which is going. With regards to quantum AI, the main problem is the circuit depth. It's like even if we have an achievable qubits, the amount of quantum circuits which are required to understand the quantum neurons is very large. We can't just directly scale what we did on an artificial neural network to put directly on a quantum processor. It's like it's like we are again trying to put a classical processing thing on a quantum processing unit, which is not how the way it should work with. There is a different math that should work in this regards. Like we want to harness the quantum power, the quantum speed up. So to harness this, there is a coexistence, which I believe is like there are particular ways in which a classical is faster, but then some certain aspects, like if we can put a data in a superposition, there's where a QPU can take place. So recently we had a talk from Sophia. She's from CERN. She's the head of this whole quantum technologies over there, and they she got a very good result over there at CERN using quantum AI. But then the major problem, which I think is discussable over here, is that the first of all, the number of qubits which we need to actually do a quantum AI, and over which the circuit depth is also crucial in this aspect. So having a good circuit depth with less error is is something which we want to achieve. And I think right now the IBM's roadmap is also towards achieving more towards this thing rather than having n number of qubits. So yeah.
How did you get into this field? Like, two things. First of all, I am really interested in getting to know about what was your initial knee jerk interest in this field, what fascinated you about AI, quantum computing, all this jazz, and secondly, what keeps you motivated currently? Like, what are you most excited about the future in these fields?
Okay. What made me come into, so I was not into AI and stuffs. I used to really love programming, and I love math. So even then I started to gain interest in physics. So there was one video by Mikaku Kaku on quantum computing, and how he was telling how quantum computers are using electrons to just multiply stuff. So that thing just built an interest. I think I was in my grade 10th or 11th when I just saw this video, and then I was like, oh, okay, this is a field which I want to pursue. And by the time when I was in my first years of my bachelor's, I was like, oh, this is great. And I found a professor. His name is Dr. Ashwath Babu. He's from Triple IT Harvard, and we got along very nice. And he became a mentor. He is a very good in this field of quantum information theory, and he through that rapport we built up on the whole thing. He taught me everything, and my college supported me in this field, because when I started this, that was in 2020, the field was just taking up. Not many people were coming into quantum computing. So that's how really I got started. And then the technologies like Qiskit and Penillion took a role of making me understand very well with regards to integrations and stuff. With regards to AI, I would say maybe I just came in because of the trend of AI and how it stuffs. But then the thing that kept me going is how challenging and how fascinating it is. It's not just about like we just take like X train, Y train, and model dot fit. It's about understanding how the functions work and for what exactly the complexities are, what exactly the problems are, how it is trying to solve it, rather than just okay, it is solving it, not making it like a black box. So that motivated me in AI. Uh, by further going is like I want to work in this field of quantum machine learning, which I feel that that there is a um, there is a high chances of how it could enhance the field of AI and machine learning towards more towards the sustainability part, because there is a need of harnessing this quantum power exactly, and this could actually help us reducing in the time of uh, I would say the speed up, like it will increase the speed up time, and at a certain level the resources which we will be using on a quantum processor will be far less than what we are using right now on a supercomputers or a data centers. So yeah, I think that's main motivation of my of like, because AI is the future, and quantum computers not just for optimizing, it could even help in this field, and it could help in sustainability, because our earth does need sustainability right now. So yeah.
This was something that when I was talking to Dr. Otwin Hess, he did go quite deep into talking about the sustainability issue for energy required to support the quantum technology as well as the AI domain. And going a little further upon that, what currently are the what currently is the work being done in the sustainability field, like whatever you are familiar with, to make sure that this sort of energy crisis in regard to fueling these technologies is being met or dealt with.
Oh, okay. With regards to like, let's talk about the classical part. I think many companies, many institutes are working towards this, making chips which can actually run AI in a very power efficient manner, uh, or like having the A6 or things which is just there for this kind of a processes, and are able to save a lot of energy in this aspect. So this is a one aspect which I see is going on. The other aspect which I talked about is the quantum thing which should work in. Yeah.
You also mentioned two things that I would like to talk to you about a little more. First of all, you said that you always had an admiration for mathematics, and I personally believe that, and you'll agree, of course, that maths is the fundamental platform or the backbone of all these technologies, especially AI, which is or deep learning, which is entirely dependent upon the models that are built using mathematical concepts and frameworks. My question to you is, how are these models built from the complete scratch using maths?
Okay. Uh, so I think I could answer this in a very basic format. Is like there is a given x is our input. Okay, and what I said before is that we need an f of x to find out. We need a function that basically tells us that what exactly our f of, let's say, x1 value is. It has to predict what of x1 value is. So we are devising algorithms based on that thing. So let's say when we come to a a simple linear regression problem, what is this is what a mapping is. Then a back propagation is again a loss function which we are trying to optimize. there is where again the math lies, where we're trying to imagine that a given model, how does it has to go ahead based on the input, and what parameters it exactly has to update so that it achieves the given f of, let's say, x1 value of it. So that's the main motivation behind going from like an input model, like for the AI. So this f of x could be like anything, and the AI role is to approximate what this exactly f of x is. And people are utilizing this f of x in various formats so that they can like build multiple f of x and then like uh, have a given output. So yeah, I'm just explaining this thing in a very vague manner. I'm just not able to come up something in my mind in which I could just explain you in a very deep format right now. So yeah.
But I mean, what I think that you'll be able to give some really good advice about is how can people get better at mathematics? How can they strengthen their fundamentals in order to finally be able to pursue research in the area of machine learning or deep learning, where they are actively required to utilize the concepts of maths to build such frameworks?
Okay. So I'm not an expert in math, I would say, but as a person who likes math, who likes doing math, people should like not just adhere towards the fact of outputs or how the whole algorithm works. It's like really understanding the math. It's like trying to do, okay, now if this is my input or this is my x, how this f of x is actually being built upon, or how this process is going to take place. Can I do it on paper? Okay, if I am saying an SVM algorithm, oh okay, so given my inputs, can what is, how can I just have an soft core margin, hardcore margin, and stuff, for what exactly the equations are at? Then you can just understand, oh okay, this is how it is working, so that you can just get into all of these things. So yeah, so in this thing I would say like my professors also did play a very vital role in making me understand on like how it's not just the programming, it's the math and the programming. So I think people should go ahead with understanding through just trying to solve it by themselves. It is difficult, it's not easy, but once we get a knack of it, it becomes very intuitive later on how things are going to work later.
You also, the second thing that you talked about was quantum machine learning.
Hmm.
How does this work? Like, if you had to give a complete breakdown of the entire rigor that goes to develop quantum machine learning, what is it? Like, explain to me the entire process for somebody who's got no context about it. Like, for the listeners who are novices or amateurs in this field, what is it really?
Okay, exactly. So quantum machine learning right now, what the trend goes in is like putting on the machine learning algorithms on a quantum platform or using quantum operations to do so. So I'm assuming right now the public knows what an artificial neural network is and what quantum gates are. So if in that regard, so there are something known as a parameterized gates, uh, and there is something called as an unitary in quantum computing. So a and parameterized unitary is something which acts as a function for us in a quantum machine learning model. The way I was telling AI that there is a function f of x, so in here in regards it comes of u of theta. The and in our quantum machine learning part, we try to approximate this u of theta. Okay, so we are trying to understand what an exact unitary would be. So given that input, we will have a given output. So what this u of theta could be? It tries to learn by itself. So this is a simple trend which is going in quantum machine learning, but this is not complete quantum machine learning. There are various different methodologies that are working. This research is very going ahead. There is a lot of things that are working in. Simply, I could say, like, we one could even explore in the exactly the encoding techniques. How can we encode a classical data on a quantum data? There are few encoding, like amplitude encoding, phase encoding, and stuffs. But what is the one which is really helpful? Then what exactly kind of a unitaries are really required to do so? What methods are there? It's like we it's easy to assume that there exists an f of x, but we don't know what kind of a format this f of x could be. So that is the whole research that goes on. Okay, so yeah, so answering the question at the end, at what exactly quantum machine learning is, it's in a very simple term, it's understanding what an u of theta is, and then optimizing the theta parameter to make it learn what the approximate function in a quantum machine learning model. Yeah.
Two major things that either of these technologies, maybe machine learning algorithms or deep learning frameworks, that they are utilized for are generally optimization challenges and pattern recognition. What is the current, or what are in general the applications of these problems? Like if you had to define optimization problems or pattern recognition issues for somebody who is not able to comprehend the actual real world application of these, could you give a real world parallel of them, and then how these algorithms are utilized to actually solve them, that process?
Oh, okay. Okay. Let me start with the optimization part. Let's say you want to go from a place A to place B. Okay, and uh, okay, let's say you are in Mumbai and you want to go from like Powai to, let's say, Dadar, and now you don't actually, and there are multiple ways to go there. There are multiple routes to go there. So right now, what would be an optimized method to do so? Is something which an AI problem could solve, something which a quantum computer could solve. Finding the shortest way is what an optimization is. As a utility, a company could be like, let's say, Uber. Uber is going to use this kind of an algorithms to leverage that, oh, there are multiple drivers who just want to take you from place A to place B, but which is the correct person, or which is the correct driver, so that it is optimized not only for you but also for the driver to take you from place A to place B. So that is an optimization problem that is there. And in the pattern recognition thing, it is again understanding, classifying that what kind of the drivers are, basically like what kind of a pattern they see. Oh, there are like, oh, there is a particular driver that actually is around, it stays from that area of one, let's say, the which I say the Hawaii, and there's the other. So that he travels there. So classifying that, okay, these are the certain numbers of drivers which actually commute from place A to place B, or is feasible for them because their home is nearby, or maybe they prefer because of there is less traffic, which is not the case. But yeah, that's usually how things works on. So I don't know if this is a very good example, but this is something which is coming in top of my mind right now for an optimization and pattern recognition, where it tries to understand, because with things in life, many things in life just goes under like a certain patterns we see, and these patterns are not completely repetitive, but mostly are repetitive, and we can just estimate this.
Also, the mathematics or the theory behind building this, actually, from a programming point of view.
Okay, in the programming point of view, so basically we use so mathematically one would start with linear algebra, given an x input, and there is again the f of x. So now what we are trying to find out, let's say there is a linear function, that's like f of x is equals to ax1 plus bx2 plus cx3. That is, the whole function is depending upon the three inputs, the x1, x2, and x3. Now we need to find exactly what the values of a, b, and c are, so that we can actually define an f of x. So it's like, given any input of x1, x2, and x3, uh, I will have a proper f of x value. It's like a, a graph, and in a graph, I just want to draw a straight line. Maybe not a straight line, it could be a curved line or something. But for simplicity, I'm just telling you there is a straight line that is existing. So I know there are a few points in my graph, and in these few points, I can try to estimate the coefficient which are responsible for actually stating how the line goes. So given there is another input value, how good it could estimate this. So in the programming perspective also, you can just program such an equation using Python. Very simple. So yeah, so the whole thing starts from here, and then the different models are built upon like this basic concepts.
Since AI is at a stage where the technology is accessible for public use and can be utilized in the everyday life maybe ChatGPT is a brilliant example of that. How AI is something that is available for the masses to utilize to make a positive change, at least in uh, idea, and better something may be a problem, a pain point, or a challenge. My question to you is, during research or studies, how can studies in the sense scientific studies, during researches or curating scientific studies, how can a researcher utilized AI to sort of smoothen the entire process?
Okay, so one basic thing is like the simple understanding stuff. Now, as a researcher, one could be like going towards how, okay, so there is this thing, instead of me googling and going and understanding and then summarizing the whole thing by myself. Well, I have ChatGPT. I could just, well, it can search over the internet. It can even summarize the whole thing for me. That's how it's gonna help me. And even finding out, doing a bit of a literature review on, like, not exactly a literature review, I would say. It's like understanding what different aspects are. That's where the AI is gonna help. It will just fasten the process of the research, rather than, I would say, contribute completely towards the research. Like, people are not now spending a lot of time over, okay, going to Google Scholar, reading. Yeah, you need to read the whole article to understand, but before understanding, it's like when you read a research article, like, this is what I follow, is I go through a multiple reading so that I can have a good understanding over the research article. But then if there is someone who could just give me a gist about what the whole article is all about, what the different sections are talking about, then I have an understanding, okay, this is what it is trying to tell me, and in a simple terms, or in a terms which I want to understand, or does any of the context which I want to relate is there in the part of that context. Like, oh, okay, I'm saving time over there. And then it is just reducing my efforts in actually reading the whole thing or getting into the research and whole point of view. So right now I just see this chat gpt is in that format of which helps the researcher in reducing the stress of complete reading, or it is reducing, it is actually mapping the real knowledge which you required, and not wasting your time in things which is may not be required for you. So yeah, that's how right now the researcher is helping. I myself have not that experience over, like, not have not seen other ways. Maybe there will existing people maybe using it in other ways, but this is something which I have seen. So yeah.
In sort of a continuation over this thought trail, what are the greatest challenges or roadblocks for the youth of today, or maybe the upcoming generations, to sort of be able to actually harness their entire potential, individual potential,
With the help of AI, right? Is that your meaning?
with the help of AI, or even in general? Like, what do you think in general are the current roadblocks for the youth? May it be the access of information or the choice paradox, where there are just thousands of choices to choose from, and that puts you in a paralysis sort of state. So, what do you think, in your opinion, are some issues in this regard?
I think, firstly, with regards to information, there is abundant information in this. We have internet. With regards to choices, yeah, there are a lot of choices. Then it's like people make choices based on what comforts them, or maybe what they have been listening to, rather than just reasoning out. I think that the first question that every youth should ask is like, why this is happening? Why should I be accessing this? Then it should be like, how is this going to be helpful to me? How can I process this? Rather than just following the black box. It's like, oh, this is what is going to give me the answer. No, you yourself need to reason out things that, okay, yeah, this may give me the answer, but then why is it giving me such kind of answer? Why is this answer which I really wanted, rather than just having a blind faith over everything, like running behind, oh, yeah. So it's like, why should I be the basic thing is, I think it's like, if everyone just starts to reason out why should I be doing this, it's a simple thing.
Another aspect that I would like to talk to you about is the utmost ceiling of the advancement of artificial intelligence. You know, building a super intelligence. That entire conceptualization, that's what I would like to discuss about with you right now. What are your opinions? How far are we till we reach that point where AI sort of becomes sentient? Like we are able to actually build a synthetic consciousness, possibly.
I don't have much knowledge about all of these things, but I could just tell you one thing, which I have heard of is, the company Quantinium. I don't know if you've heard of, and the Oxford. What these guys? So there is this professor, not professor, like he's a scientist now, Bob Cook. He's in culture Quantinium, and I think I have heard from one of the person who has worked with him, that this Oxfords and everyone, they're just trying to look on this something called as quantum consciousness, of how we could map consciousness into a quantum processing units, because there is a field known as quantum natural language processing, which tries to harness the whole stuff. So uh, in the same regards, like, they are trying to map how can we map consciousness onto AI, and since these are whole as a quantum processes, they are trying to put it in that term. So can we have a quantum consciousness? And maybe that could be an answer to the whole thing, because as per my knowledge, there is like a lot of research that is need to be done, even in regards with the classical systems and all. And as one article says that our brain is a quantum computer, well, then maybe it's like the consciousness also can be mapped through that thing. So yeah, maybe a quantum computer would help in that.
What are some other applications of quantum technology or quantum computing? Like I would like for you to talk about probably drug discovery, or maybe you know different other applications, probably in a little bit of detail to actually have the viewers get an idea about the actual impact that the quantum technology can have on the society at large.
Okay. So basically, right now, whatever algorithms which we are using and having there in classical, they come to a saturation at a point because of this large amount of data, and there is a exponential time that is required to process all of these things and stuff. So right now, the quantum computers could be very much utilized towards this. Firstly, the optimization problems, in which one would be like the one which I sold the example of the Uber, of optimizing the path. Oh, then there could be maybe like handling the air traffic, designing engines. So, there's a company known as Boson QSci, which I have worked with as an intern before. They work on this computational fluid dynamics, and they are working very well on this quantum algorithms uh, for this dynamical processes. That is where it is also going to be helpful. Then the second lead could be like in material sciences of why we struggle of understanding, like as Dr. Feynman said, that if we want to replicate the world, let it be quantum, not classical. And that's where the quantum computing comes in picture. It's like we can simulate the quantum processes on an actual quantum hardware where it could actually behave in that similar fashion. That's where the drug discovery comes in picture, or various material science applications comes in picture. I think like this is one of the most prominent thing which right now the whole world is working, because we see that even if we have Google's AlphaFold and stuffs for protein recognitions, and there is still a lot of aspects to work on, and that is where the quantum computer is going to take come in picture. uh, so I think I see right now is just this algorithms which it is trying to work on, and that is where the whole application is. It's going to be in a broader aspect rather than solving simple things in life, because well, classical computers are already solving those things. And uh, that I think that will be like, I'm not sure if ever a quantum computer will come into the classical picture, but hope I'm not don't know. It's a very wide research, and it's very difficult to predict the future.
You did mention about the inclusion or the utilization of quantum computers in the aviation or aerospace sector. Uh, could you elaborate upon it? Like, in what specific ways is quantum computing or quantum technology probably contributing towards the betterment of our current know-how in regard to aerospace?
Okay. So right now, like when it comes to in these fields, what we see is all the models which we build. So I'm giving a very broad aspects of this, but any models which we build are again based on some partial differential equations, and finding the solutions of this partial differential equation is not that easy. It's not that trivial to get into. So here's where the quantum computer comes in picture. It tries to solve this kind of an equation. Like we have various classical algorithms, but the solution is not an exact solution. It's again an approximate solution. So quantum computer over here, like we believe theoretically that it is possible to achieve a global minima, or something. I'm not talking in a very kind of thing, but it's like it can find a very proper solution towards this partial differential equations. So that's how it's going to take in picture in terms of aviations or other things.
Do you know about Gravity Industries?
Gravity Industries now.
I'm going in a little bit of side tangent, but since we were talking about aerospace, they basically, Richard Browning is the CEO. The last I read about them, and their entire purpose is to sort of scale down the aviation technology to replicate flight systems for individuals, like jetpack technology, sort of, but a
Hmm.
little more advanced in ways. And my point with going onto the side tangent is how the end purpose or goal of any technology is to sort of scale it down in terms of its physical size. Like with classical
Okay.
computers, when it started in the 1900s, they were bulky and huge and everything. And today it's like we have palm tops and our mobile phones, right? We have Apple
Hmm.
watches. With Meta, they release their lenses, smart glasses, Google. And as we move forward, currently quantum computers are bulky and huge and hefty, but there will inevitably come a point where possibly we might have quantum personal quantum computers. My question to is, we did talk about how classical computers already are capable enough to satiate our current requirements, day to day requirements. And quantum computers are good for explicit specialized problems, but not necessarily the generic day to day tasks. If we are to reach a point in time where we have these personal quantum computers, what would they be used for, if for anything at all?
It's completely depends on the fact that, like, firstly, your classical computer also works on the basis of quantum mechanics, and the only thing is it works on a simple information theory rather than quantum information theory. So right now I don't see the point of, even if we have a personal quantum computer, maybe at most for gamers it will be like, oh, much faster processing unit, I can run a game in a very more realistic manner because it is able to find the equations, much like solve the equations, vector equations very faster, and process the holographics very faster. Yeah, that could be a there. But then maybe it's like, I don't know, if I want to use an MS Excel sheet, I don't need a quantum computer to do so. In my classical computer, an i9 processor is very very fast to do so, and it's very helpful.
I mean,
So
they could be more of use, uh, probably in for astronauts maybe, or people who are working in extreme conditions, like astronauts. They are in space, right? They might be able to utilize more and gain more benefit from using quantum computers. Maybe if we reach the potential or the point in time where we are able to, where things like interstellar travel and multiplanetary mutation, it's day to day normal things. They might be of use in that regard, like in those extremities. But I think I understand, day to day lives for people, for a normal person, quantum computers might not really change much.
yeah, it's unless there comes a product which actually is something which is very unimaginable, and it's like, who had ever thought that there will be existing something called as a mobile app. Okay, and that could revolutionize things. So this is a very very interesting research, and it is going to take time, but yeah, if it could do something, it's again, we are reducing the latency when we come to the point of accessing the quantum computer in hand or in person. Right now, even as everyone can access a quantum computer, it's like it's accessible through the cloud. You just need a classical system, as a good internet connection, and proper timing to access a quantum computer. So yeah, I think current day-to-day scenarios, a classical computer is solving it, and it's like, I'm myself, I'm happy with my mobile phone doing so many things. So yeah.
How do you think, what after this, like AI, quantum computing, right, achieving super intelligence, whatnot, what then? Like it's a very futuristic question, and it is in no way required as of now in terms of practicality. But like, just to think, right, probably drive a different thought trail for people, just to make them think, because we did talk about how thinking is important, right, for today's generation especially. Have that critical thinking and that knack for asking to reason, right? So in just in that same breath, what after that, do you think?
Oh, it is like, have you seen the movie Wall-E?
Yes.
Yeah, yeah. So you could have seen how people have just got so comfortable with everything and
Right.
all. Yeah, but I think the question comes, if we have achieved everything we can in this world, every possible things, then the thing is like, what we want to pursue is the question that we comes around. Human curiosity is still gonna be there. It's always gonna try to pursue beyond the limit of whatever it can achieve. And if at the point when we have solved everything, it comes more about uh, doing what we love or the passion is. But then again, the question comes: people love exploring things. People are very curious, and that loops is just gonna be there. The whole understanding is gonna be there, and so maybe the world will be more towards optimistically. The world could be like they would be trying to maybe engage in different activities to keep themselves busy or something, occupied, and be happy all about it. So yeah, there's a lot of things to talk about these things, and it becomes very controversial. There is you could put spirituality into all of these things, and yeah. So I would it's in my mind it's very difficult right now to like give you an exact thing what exactly could happen, but on the top of my mind, this is something which I would say.
We've talked about a lot of far-fetched concepts, so to speak. Uh, Coming a little back to the pragmatic or the current uh, state of things, for somebody to who has an interest in these fields, right? What would you suggest them to as a step-by-step approach to build an expertise and comprehensibility in regards to these domains, because they are very technical and scientific domains at their peak. So how does one from step zero build a mastery in these fields?
Okay, I would firstly say get your basics right, and by basics I mean the math. So having an I'm so sorry. Having a basic understanding of how exactly the basic math works, which supports it, is where a person should start with. And even the person, it's like not get into a deep understanding of all of it, but understanding what classical other kind of systems exist and what other kind of solutions are. Maybe not in the starting process, but yeah, that is also something which is required. It's like why I want to do AI. That's the question that comes around. So this is also some understanding which someone, as an individual, someone should have. So yeah, getting back on track. Firstly, it's like getting the math right, the whole thing. Then the corresponding technologies like understanding Python, what different frameworks are exactly. Then going again back to some theoretical aspects of how things are actually built upon, and then actually practically implementing those with the frameworks which are actually available. This whole process is something which could help them to get a mastery. Like this is what I am following, and I myself am not a complete master in all of these things. I have an experience. I'm not a master in all of these things, but it's just keep on doing this. The whole process and getting an understanding of whole thing is going to be very helpful. Um, yeah, and I think there's not like a particular pathway. People may have a different outlook towards it, but the only constant thing is understanding the basics, understanding the core concept on what it is built on is what is required. So yeah, that's if someone could master that and then move ahead with other mastery, it's what they could do. Yeah.
Also, we were talking about this a little while back, but coming back to it, just to explicitly mention this, in regard to quantum hardware, how is it done? Like, we did talk about the breakdown of uh, frameworks and algorithms and the software aspect, but to give us step-by-step description of quantum hardware, its assembly, how is it built?
Okay, so I'm not a complete expert in these things in quantum hardware, I would say, but as per my knowledge, so there are like various platforms in which a qubit could be realized upon. So one of the famous ones is a transmon. Then there are photonic traps. I'm sorry, trapped ion based quantum systems. Then there is something by D wave. I'm not sure if I'm pronouncing it correct. It's called fluxions, which is also a similar kind of an system, one which it's also a superconducting system, in which, so basically when we come to building the quantum hardware, it's like the first layer is what we will need is a qubit, an actual realization of a qubit. So we could have, so one could say a qubit is nothing but an oscillating particle which has a different which follows, which should behave like an atom. So what right now we have are the artificial atoms which behave like so it could have a different, it should have a ground state and excited state. So there are like there is something known as, there are six criteria of building such a quantum hardware known as the Da Vinci criterias. I'm not able to recollect all of them in my mind right now, but so on this criteria you could actually state how a qubit is built. So the next phase is comes is the communication of these qubits, of how you could operate them. And so there are various cavities and various uh, uh, I would say very various ways of interacting it. You could have like a resonators and stuff where it could actually help in measurement, which is actually turns in a transmon based qubits. So so this kind of a thing is there. Then the refrigerator which you see in a quantum system is actually just to have a superconducting level, but then the whole wirings are nothing but the microwaves, the electromagnetic waves which are communicating with this kind of hardwares. So that is the thing. So you have a classical system which will produce instruction in terms of pulses are nothing but this microwaves, the electromagnetic waves, which goes and interacts with the system which we have created, which is the qubit, and does our operations, and then give back a result, which is again in terms of the microwaves, and we again read it. Uh, we read it, and then we get our values. So that's like a very broad way of describing how the quantum hardware works, but it completely depends on various kinds of hardware. There is much into all of this. There is a lot of physics into all of this. So yeah, I'm not getting into deep into that, but yeah, this is exactly how it works. It's like you have a control unit. The control unit just talks with the quantum processors. The quantum processors use an output back to the control unit. The control unit then talks with a classical computer. So this is a simple way of how the quantum hardware process works out. It's same kind of like what our classical systems have worked. They also have a control unit. They have CPUs, GPUs, and stuff. So yeah.
How do you determine which qubit technology is the most apt for the quantum computer that you are building? Because there are quite a few variants in them as well. So how does one determine?
Well, it basically depends upon the your need. I would say, like if you're working on an optimization problem, I would say right now the D waves quantum annealers are way too good for optimization things. And well, then maybe you could have for faster operations, you could rely on something called as a superconducting qubits. And if you want a high retention of an information, the trapped ions have a very high fidelity rate. But there are even other technologies like the nuclear magnetic resonance ones are there, the NV centers. I have not completely dealt with this kind of technologies, but I have heard that they are very good. And exactly selecting a quantum platform is still an question to answer by many in this world. And if no one, I'm not sure if anyone really knows, and like there could be very mixed of opinions on this. I myself am not uh, I would say I'm not the right person you should ask which quantum technology is where to use when. I mostly work on this algorithms point of views, but Yeah, it's still in a part of research of which kind of a quantum technology is going to be the at par. But right now, as I said, like D-wave annealers, then Rydberg atoms, these all are performing, and they have their own trade-offs. And so based on your requirements, and can you handle those trade-offs or not, is what the whole thing is working around. So yeah, I don't know if I'm completely answering that question, but this is what I know.
Um, to sort of end this theoretical segment of everything, what goes into building a qubit technology? Like you did sort of were able to explain why certain qubit technologies are chosen over others, but like how is how is a single qubit technology built for that matter in the first place?
Okay. It's yeah. You are mean to say is like how are we realizing a qubit?
Yeah, how are they physically realized? Like how do we know what to do with them, and how to sort of, yeah, how to physically manifest them, like with topological quantum computing, for example, the qubit technology. A little while back we didn't know how to realize majorana fermions, and suddenly we were able to get them to work, and we realized how good they were at doing what they were. So like how
Yeah.
do we do that? Is it just a trial and error thing, or are there typical approaches to doing that? Like what is it?
Uh, yeah. It's not completely trial and error thing. It's like it's an calculated trial and error thing, kind of a stuff. But so I think if I will can just answer the question on how can we realize a qubit just on for the transmons, because I have a bit understanding over it. So I'm not sure if the audience would be knowing of LRC circuits, an inductor, resistor, and a capacitor circuits. So these qubits are nothing but, as I said, are the oscillating particles with the different energy levels. So what these transmons or the superconducting qubits try to do is they have this LRC circuit so that they could replicate an oscillating behavior. If anyone has ever worked with LRC circuits during, I don't know, it's for the Indian audience who have given JEE, are very much known to the LRC circuits and different equations, and how can we have an LC oscillations, a damped oscillations kind of a thing. So usually this is the basic concept. They try to just build an LRC circuits, and LRC circuits is something behaves like a qubit because of its oscillating behavior. But the catch comes is that if we see an LC oscillation equation, it's an harmonic oscillation equation, and when we try to do that, we have a discrete energy levels with similar energy gaps. Just so to avoid this thing, people use something known as Josephson junctions. The Josephson junction gives a non-linearity in the magnetic field, and which helps us in realizing an atom like a behavior of different energy levels. But since we are working with qubits, that is two energy level system, we are only concerned with the first excitation energy and the ground state. So that's how maybe a qubit is realized. It's just an LC oscillations. But again, the inductor here is a Josephson junction, which is actually playing the vital role here. I don't know if this kind of help answers the whole thing or.
I just have one query. I did understand what you were trying to explain, but just probably taking it a bit further. After realizing these qubits, how are we able to how are we able to use quantum programming, of like how are we able to use programming to sort of control them? How is quantum programming different from normal classical programming? In what way? Like what goes into being able to control these qubits?
Okay, so again, we are controlling this qubit, as I said before, using microwave pulses. So when we write this pulse, okay, yeah, I think I missed this one. So let's say when you are writing gates in your Python program, this goes down and converts into a CASM program. This CASM program just puts it let's say on a controlling unit. What this exactly controlling unit does is tries to realize these gates on the microwave pulses. So we have qubits. It's an atom which is interacting. But now, how are we going to put this gate operations? These gate operations are realized as the microwave pulses of frequency of the microwave pulses which we are putting in. That acts like our Hamiltonian. So when there is let's say a, a microwave pulse oscillating in like maybe with an oscillation of pi or something, uh, we could have a certain kind of a quantum gate in that. So that operation is put on a qubit. So let's say our a whole LC circuit is in a ground state, and when we put this microwave pulse, it maybe it tries to goes towards an excite. It acts like an X gate. It goes from 0 to 1. So in this, we are trying to put on the quantum operations in picture. So that's how when we write gates in Python program, this Python programs get converted into this microwave pulses. So there is this aspect, if anyone wants to read, by Qiskit Pulse, if anyone has heard of or you don't know. So this is how you can actually control a quantum hardware.
And that is why, like, as we try to scale it and bring about more and more qubits, it becomes tougher and tougher to sort of have them collaborate and synthesize with each other. Right. Okay, right. It's really interesting, like when you start wrapping your head around the basics and everything. But right. The last and final question for this amazing conversation that we had, a very thought provoking and intriguing one at that. What is your piece of advice for humanity? Like, what would be your piece of advice for humanity and the generations to come?
Well, I myself am a 23-year-old individual.
Oh, I know. I'll also share with you the motive behind that question. I I have this idea that I've I've harbored this notion that humanity and the human race are two separate entities. Like, human race needs to harbor humanity in the long term to sustain its existence. It's sort of how it's a moral and ethical sort of domain. It's a moral domain, but that's why because umpteen times people feel that technology or science is shallow and completely has to do with logics and rational and just all that stuff. But behind every scientific innovation is a stance to impact humanity for the better. And which is why I asked you this question: what is your advice for humanity, so as to remind people or not to have them forget that science and technology is based into this notion of the betterment of humanity before anything else.
Oh, okay. So, as per my experience till now, till I have grown up and what I have read and think, maybe my so I would really say this. Maybe my answer will be bit biased because I had been following something in spirituality and stuff. I have this reading because it intrigued my mind. I found it logical. So my answer is would be like instead of running towards an output based answer, it's like just for pleasure or maybe having things for like instant happiness or things like which doesn't have an everlasting effect or maybe is not reasonable. The humanity shouldn't pursue that thing and should have a simple moral ground on just asking the question why is this is it really necessary? Is it really needed for me? Is it something which I want? Can I do, like, it's just about questioning and retrospecting ourselves again, and this time, yeah, not overdoing everything, not going under doing everything under impulses, because I think very worldly problems comes around. It's like they have like egoistic issues, superiority issues, and those kind of a thing. So maybe it's just a simple understanding, having an empathy towards things you approach, and just reasoning about why this happens. Maybe that would help, and coming into a logical solution after that is with an empathy is what I would give an advice to. But I seriously don't know the real answer
I mean,
towards
I'd
what exactly.
really say that it is a very something that people can imbibe into their day-to-day lives and feel a difference in each and every aspect and facet of their individual existence. So I feel it's a good advice. I mean, subjectively and objectively speaking, it's pretty good. But yes, Mr. Gaurang Belekar, thank you so much. It was a lovely conversation. I enjoyed it. I really enjoyed it.
And yeah, thank you so much for inviting me. And this is morning time over here, and it was great talking to you, and I really enjoyed this conversation as well. So thanks for inviting.